Hello, I'm Arsenio Nicolas Jr. and together with Andrei Insigne, we'll present to you today our project. Now, this project aims to segment customers using clustering techniques, particularly K-means algorithms. We work with an online retail dataset containing invoice-level transaction records from 2010 to 2011. Customer segmentation helps in identifying different customer groups, allowing businesses to apply targeted marketing strategies and improve customer retention. We researched two main clustering techniques. First is the K-means. K-means is a centroid-based clustering technique. It groups data into K clusters by minimizing the distance of points from their assigned cluster centers. It is efficient and interpretable, making it ideal for business use cases like marketing. And we chose K-means because the project requires clean and simple groupings for business use. And K-means is fast, easy to implement, and works well when clusters are distinct. Business stakeholders can easily understand and apply the results. For DB-scan or density-based spatial clustering, DB-scan forms clusters based on density rather than distance. It is good at identifying arbitrarily shaped clusters and ignores outliers. The reason we didn't choose DB-scan is because dataset has varying densities and noise. DB-scan is sensitive to EPS and mean samples, which are hard to tune here. K-means gave better and clearer business segments. We loaded the dataset year 2010 to 2011 that CSV using pandas. The dataset includes invoice, stock code, description, quantity, invoice date, price, customer ID, and country. We examined data types, missing values, and basic statistics, and a total of 541,110 rows were present. And for the data cleaning, to ensure model quality, we performed the following steps. Converted invoice date from string to date time, drop rows for customer ID was missing, removed cancelled orders and negative quantity or price, cleaned up text fields by stripping white spaces. For RFM analysis, we created these features. Recency is equal to the number of days since the customer's last transaction. Frequency is the number of transactions a customer made. Monetary value is the total money spent by the customer. Each metric was calculated by grouping transactions by customer ID. Clustering algorithms are sensitive to scale. We use standard scaler to normalize the RFM features so each contributes equally. And to find the best value for K, we use this method because this helps identify the ideal number of clusters K by plotting the within cluster sum of squares or WCSS against different values of K. WCSS measures the compactness of the clusters, specifically the sum of square distances between each data point and the centroid of its assigned cluster. Lower values indicate more compact and well-defined clusters. As shown in the graph, the WCSS decreases rapidly from k equals 2 to k equals 4. This is expected because as increasing the number of clusters typically results in smaller distances within each cluster. However, after k equals 4, the rate of improvement in WCSS slows down significantly, and the curve starts to flatten. This point of inflection or elbow indicates that adding more clusters beyond this value yields diminishing returns. And therefore, based on the shape of the curve, we selected k equals 4 as the optimal number of clusters. This value offers a good balance between model simplicity and cluster performance, helping us avoid both underfitting and overfitting. For the evaluation, the interpretation of the silhouette score closer to 1 means good separation. And in this project, it showed 0.62, while the Davies Bolden closer to 0 means better clusters, means this one's 0.75. Now for visualization and interpretation, we used PCA to reduce RFM data to 2D. Since our original dataset had multiple dimensions, recency, frequency, and monetary, we applied PCA to reduce it to two principal components, PCA1 and PCA2. This allows us to plot and visually inspect how well the clusters are separated. Each point in the plot represents a customer, colored according to the cluster they belong to, with cluster 0, 1, 2, and 3 labeled accordingly. We can see that the clusters are fairly well separated in 2D space, indicating that the model has effectively grouped with customers with similar behavior patterns. And here's how we interpret each cluster. Cluster 0 is the dark purple, and these are moderate customers. They shop less frequently and modestly, but they are still fairly recent. Cluster 0, the light purple, and these are inactive or lost customers. They haven't made a purchase in a long time and buy very rarely and have the lowest spend. Cluster 2 or the green, and these are the VIP customers. They purchase very frequently and spend the most and have very recent activity. Cluster 3, the yellow, and these are the high value loyal customers. Their recency is also low. They purchase regularly and spend over 12,000.
So moving on to part C, which is market basket analysis using association rules. So let's look at how we can find hidden relationships between products with market basket analysis. So the main question we're trying to answer here is simple. What products do our customers frequently buy together? So answering this is key for smart business strategies like product bundling, cross-selling, and even how to lay out a store. So to do this, we used a classic algorithm called a priori. The logic behind a priori is really intuitive. So it works on the idea that if an item set like bread, milk, or butter is frequently purchased, then any smaller part of it like bread, milk, must also be frequently purchased. So this allows the algorithm to efficiently find patterns without checking every single combination. So going back to our pre-processing for association rules. So the first step in our code was to transform our raw sales data. So we converted every customer transaction or basket into a format where each row represents one transaction and the columns are all of our different products. So the values are either a 1 if the item was in the basket or a 0 if it wasn't. So going back, so with our data ready, we ran the a priori algorithm to find frequent item sets. Then, we used these item sets to generate our final association rules. Now, to understand these rules, we need to look at three key metrics. So, first is support. This just tells us how popular an item set is. A support of 2% means that the items in that set appear together in 2 out of every 100 transactions. Second is confidence. This tells us the likelihood of buying a second item if you've already bought the first. For example, a confidence of 70% in the rule, bread to milk, means that 70% of customers who bought bread also bought milk. But the most important metric is lift. It tells us how much more likely two items are to be bought together than just by random chance. So a lift of 1 means that there's no relationship. However, a lift greater than 1 means that there is a positive relationship, and the higher the lift, the stronger the relationship is. So this chart visualizes all the rules that we generated. On the x-axis, we have support. On the y-axis, we have confidence, and the color and size that each dot represents is the lift. So the rules we're most interested in are those in the top right with the brightest colors. So as they have high confidence and high lift, so based on our table for the 5 actionable rules, we found that uh, Dolly Girl Children's Cup and Dolly Girl Children's Bowl have a very high lift and confidence. So this means that customers who buy One of these items are very likely to buy the other. So for our actionable insights, so for product bundling, create a Dolly Girl bundle with Dolly Girl children items, vintage spot beaker, and ceramic drawer knob at a slight discount. For website recommendations, if a customer adds one of these items to their cart, the website should immediately recommend the others. And lastly, for in-store placement, physical stores should place these different items next to each other to encourage impulse buys. So moving on to part D, which is reinforcement learning. So first, how is reinforcement learning different? Supervised learning uses labeled data to learn correct outputs. Unsupervised learning finds hidden patterns without labels, while reinforcement learning learns by interacting and maximizing cumulative rewards, and it's not supervised feedback, which guides learning even without labels. So, to understand RL, you need to know 5 core concepts. Let's imagine that we want to build an agent to offer discounts to customers who are about to leave the checkout page. So, for the agent, that is our program, or the discount bot. The environment is the e commerce website that it operates in, or the checkout page. The state is the current situation. So, for example, the customer's cart value is $150 and they've been on the page for 90 seconds. For the action, that is what the agents can do. So, the customers, for instance, it could offer a 5%, 10%, or 15% discount. And lastly, the reward is the feedback that it gets. It gets a positive reward if the customer makes a purchase, and a negative reward if the customer leaves anyway. And the ultimate goal of the agent is to learn a policy, which is just a strategy to choose the best action in any given state to maximize its total reward over time. So, how would our discount bot learn? So imagine a customer is about to leave. This is the state. The agent, knowing nothing at first, tries a random action, offering a 10% discount. The customer accepts and buys the items. The agent gets a positive reward and it learns, okay, that action in that situation was good. Later, another customer is leaving with a different cart value. The agent tries another action, a 5% discount. So this time, the customer leaves. The agent gets a negative reward and learns that action in that situation was bad. So after thousands of these interactions, the agent's policy gets smarter and smarter. It might learn that for high value carts, a 10% discount is highly effective, but for low value carts, it's better to offer nothing. So, what are the key takeaways? Reinforcement learning has huge potential benefits, like creating truly personalized experiences that adapt in real time. However, it also has challenges. It's complex to set up and requires a lot of live interactions to learn effectively. By exploring both market basket analysis and reinforcement learning, we can see how data science offers tools not only to understand past behavior, but also build intelligent systems for the future.